In this lecture, we explore the final stages in the life of stars. We will focus on how stars end their lives, what determines their final fate, and how these dramatic processes shape the universe itself. After the red giant phase, stars follow two different evolutionary paths. Low-mass stars evolve into white dwarfs. High-mass stars undergo much more dramatic transformations, ending in powerful explosions known as supernovae. In this lecture, we will focus mainly on high-mass stars. Before moving ahead, let us briefly summarize low-mass star evolution. A low-mass star expands into a red giant, then sheds its outer layers to form a planetary nebula. The remaining core becomes a white dwarf. This process is relatively short and gradual compared to what happens in massive stars. High-mass stars begin their life similarly, as protostars and then main sequence stars. However, due to their high mass, they burn their nuclear fuel much more rapidly. This leads to a shorter, but more energetic life. As high-mass stars evolve, they become yellow giants, burning helium, and later red giants, burning heavier elements, with no new elements forming beyond iron. As hydrogen is exhausted, the core contracts and temperature increases. This allows fusion of heavier elements, helium into carbon, carbon into oxygen, and eventually into even heavier elements. This continues in successive stages. At this stage, the star develops an onion-like layered structure. Each layer is responsible for fusion of a different element. Hydrogen in outer layers, helium, carbon, oxygen, and finally silicon near the core. At the center lies the iron core. The formation of an iron core is a turning point. Unlike previous fusion reactions, fusion of iron does not release energy. Instead, it absorbs energy. This means the star can no longer generate pressure to oppose gravity. Without sufficient outward pressure, gravity takes over. The core collapses rapidly. During this collapse, protons and electrons combine to form neutrons. The core becomes extremely dense in a very short time. The sudden halt of core collapse causes a powerful rebound. This produces a supernova explosion. The outer layers of the star are blasted into space with enormous energy. For a brief period, the star can outshine an entire galaxy. There are two main types of supernovae. Type 2 supernovae occur in massive stars due to core collapse. Type 1. A supernovae occur in binary systems when a white dwarf accumulates matter and undergoes runaway fusion. Both processes release tremendous energy. The final remnant depends on the mass of the core. If the core mass is between about 1.4 and 3 solar masses, a neutron star is formed. If the core mass exceeds this limit, collapse continues and forms a black hole. Thus, mass determines the final fate. The fate of a massive star, whether it becomes a neutron star or a black hole, depends on the mass of its collapsing core. Supernova explosions are not just destructive, they are also creative. They produce elements heavier than iron. This occurs through neutron capture processes. There are two important neutron capture processes. The S process, or slow process, where neutron capture happens gradually, and the R process, or rapid process, where intense neutron flux leads to rapid formation of very heavy elements. Elements like gold, uranium, and platinum are formed in these processes. Massive stars end their lives in supernova explosions. They leave behind neutron stars or black holes. And most importantly, they create and distribute heavy elements across the universe. This leads to a profound realization. The elements that make up our planet, and even our own bodies, were formed inside stars. We are, quite literally, made of stardust. The more mass a star is born with, the shorter its lifetime. Massive stars live fast and die young, while smaller stars enjoy longer lifetimes.